Okay, so for the surface area calculations, we will start with this example. The arc of the parabola y equals x squared from 1, 1 to 2, 4 is rotated about the y-axis. Now, parabola means something like this. Okay, so this is the nature of the parabola y equals x squared. But here what it says is, on this parabola you only consider a certain region only, from one place to another, and these two places are given by the 1, 1 position and the 2, 4 position. So we only consider this arc, right? So we really don't need the rest of this parabola, right? And we now, even at within this arc, we still have this relationship, right? So that's the only important detail that you can get from this sentence, and the starting point is 1, 1, end point is 2, 4. And this arc, this portion is rotated about the y-axis. So this is a y-axis rotation, right? Remember in that animation that I showed you in the previous video, it was a x-axis rotation. But now we know if we rotate it across the y-axis also, it will form a three-dimensional object. Okay, right? So, and we have to find the surface area of the resulting 3D object, right? Now remember, when it is a y-axis rotation, this is the formula that we have to use. Here you should have 2 pi x, right? Not 2 pi y. Okay, so by using that formula, we can say the surface area will be equal to the integral of 2 pi x ds. And for ds, there can be two possibilities, two options where we can use. Now we can either use this one or this one, right? And you can see that in our given expression, which is y equals x squared, it is not difficult to subject x, right? You can write x as the square root of y. Okay, so since we can subject, now in the equation itself they have subjected the y coordinate, so if we can calculate dy by dx as well as dx by dy without any difficulty. But if calculating one is difficult, then we will have to use the other, right? But in this case we can use both. So we will try to do it in both ways, and to start the problem we will start with this type, right? So that means I'm choosing this one as my dx, right? Remember, it comes with a dx term, right? Because we are differentiating it with respect to x, and also we need to integrate it with respect to x, right? Okay, so now we have 2 pi x, and remember this will not change no matter what type we use for ds, right? This only depends on whether it is a x-axis rotation or a y-axis rotation. Okay, and we are free to use whatever the option we have for ds, right? And here I am using this one, which is dy dx squared dx. And then as we are using dx, that means we are integrating with respect to the x variable, so we need to mention the start point and the end point of the x variable, which is 1 and 2. Okay, so those are the important things that you should focus on, right? Once you have figured out the main formula, then it's just a matter of differentiating and substituting the correct terms. And the integration, you can do it like this, right? Now we have the value for dy by dx, which is equals to 2x, right? So dy by dx squared will be equals to 4x squared. So here you will have 1 plus 4x squared term, and you can use the substitution method. You can substitute this one for u. So remember to follow all the necessary steps when you are using substitution. Also remember to change the limits if you are doing the substitutions, right? And then you can see that the area will be equal to this much of units, square units. Okay, to be precise, if it's better if we mention this one as well. This is square units, for example square feet, okay, square foot, yeah. And now here, see, we have used the first formula for ds, right? Now there were two options for ds, and in this case we have used this formula for ds. But now let's try to use this one as well. Okay, so then if we are using the other one, so here it will be dx by dy, and this one will be dy. So in that case, the integral should run across the y variable. So starting point should be 1, end point should be equal to 4. Okay, right. So if you are using the second formula, then the area will be equal to, still since it is a y-axis rotation, this x will not change. Okay, only the part associated with ds will be changed, right? So we have squared dy and 1 to 4. Okay, and remember x is equal to this one, so dx by dy will be equal to half over square root of y, right? And then again it's just a matter of doing the integral properly. Well, but before that, now there's a small glitch in this equation. See here, this is an integral of y, right? This integral runs through y, but we have written a x term here because it must be there for the formula to work, right? Formula to tally with the y-axis rotation, we must have x here. But as we are differentiating with respect to y, we must convert everything back into y variables, because we cannot integrate a certain integral if the variable is something else and if we are differentiating with respect to a different variable. Okay, under normal circumstances, because there are some methods called partial derivatives and partial integrations, but in normal situations like this, you cannot have two different variables, right? So what we should do is we have to rewrite everything in terms of y, and here dx by dy is already in terms of y, so there is no issue with that. But for x, we will have to write it as the square root of y, right? And other than that, we will not have any problems in computing the integral. So the integral will be like this, and you can see that you have the same result as before, right? Okay, and we have to use the substitution u equals 4y plus 1, but I have not shown the intermediate steps for the substitution. Okay, but anyway, we will end up with the same answer.